So what we found is closed surface integral of E bar dot dA bar, that's equal to Q n closed divided by epsilon naught. Am I right? Now suppose I have some volume charges, okay, in the region. I will not take point charges. Earlier I have taken point charges and I have somehow logically proved this one, isn't it? Logically proved Gauss law, okay. Now I'll take what you call volume charge density, because for a point charge also you can define volume charge density. We just learned that, am I right? Q into Dirac delta, isn't it? So that's why let me write everything in terms of volume charge density, okay. Now look at here, this Q enclosed, okay, I'm going to write it like this, integral of rho d2. What is that rho? That is the what you call, what is this volume integral? That volume integral is over the volume within the surface. Is that okay? So can I write like this? Suppose if they are point charges, you define rho as a Dirac delta. Is that okay? So can you see the board? Suppose if they are point charges, you define rho as a Dirac delta, or if it can be any other generalized charge distribution. Is that okay? I mean, now in that case, look at it. Can I write Q enclosed like this? Because what is this V? V is the volume. Suppose if you have taken surface integral like this, V is this volume. That's what I'm talking about. Is that okay? Now left hand side, look at here, according to Gauss divergence theorem, can I write like this? What this surface integral is equal to divergence of electric field d2, left hand side. Right hand side, I'm going to substitute this one, volume integral 1 by epsilon naught, volume integral of rho d2, speak out. Now again, in case of Gauss divergence theorem, what is this volume? This volume is the volume within the surface, am I right? Now this volume is same as this volume. Is that okay? To find charge enclosed, you have to do the volume integral of charge density within that one, am I right? Again, charge may be spread throughout the region, but only charges within that region does matter for us. So that's why these two volumes are same. That's why whatever the integrand, that should be same. You can write like this, del dot E is equal to rho by epsilon naught. Speak out.
Sir, in above state, in the right hand side, we wrote like the plus that rho deta upon over 1 upon epsilon naught, sir.
1 upon epsilon naught rho d2. Q enclosed. This is Q enclosed. Divided by epsilon.
Yes, sir. Rho deta is the Q enclosed, sir.
Integral of rho d2 is a Q enclosed.
Okay.
Net charge enclosed. But you should know what are these two volumes are same, right? When you convert this surface integral into volume integral, in case of Gauss divergence theorem, so what is that volume? That volume is the volume within the closed surface, isn't it? While finding total enclosed charge, what is that volume integral you take? You should take the what you call volume integral throughout this region, am I right? Because there may be charges somewhere here, nearby the surface also, in the middle also, isn't it? You have to integrate throughout that volume, then only you will get net charge enclosed, isn't it? These two volumes are same. Now we call this as differential form of Gauss law. Now look at this one carefully. Del dot is equal to rho by epsilon naught. Okay, del dot. So for any charge configuration, okay, for any charge configuration. But look at here. Look at here. This is speak out.
Sir, here we are taking two. Sir, we are taking the volume of two surfaces. First one of the Gaussian surface volume. Second one the charge enclosed the surface.
No, both are same, isn't it?
Both are same.
Both are same. One was what you call, again, according to our Gauss divergence theorem, surface integral converted into volume integral. That volume is volume within the surface. Other one was volume integral to find net charge enclosed. To find net charge enclosed, you should do the complete volume integral of the charge density, isn't it? Net charge enclosed by the surface. That is the meaning. Is that okay? Now actually, look at here. You have what you call, you have some charge distribution somewhere here, okay? some charge distribution somewhere here. You are finding electric field here, or I'll not mention at all. Again, charges are there in the space, okay? I don't know what is the charge configuration. Let me choose the origin. Let me write the electric field at this point, okay? Electric field at this point. Electric field at point in space. If I take divergence of that one, look at here, this derivative, okay, is with respect to x, y, z. I told, am I right? If you write del vector, there is a derivative with respect to x, y, z, am I right? So that is equal to, look at here, charge density at that point divided by epsilon naught. Actually, this is the correct one, actually. This is the correct one. Are you getting my point? Again, here I have written that one, del dot is equal to rho by epsilon naught. Look at that one carefully. Where you are taking derivative, where you are defining rho, these are very important, isn't it? Speak out. Now, this rho is defined at the point where we take the derivative. Is that okay? That means if we define electric field at this point, if we define this derivative at that point in space, that means divergence. Derivative means divergence, that's what I'm taking. Then you have to define charge density at that point divided by epsilon naught. But actually, this information is completely, it doesn't exist in this derivation actually. It's quite difficult. Isn't it? Are you getting point? Now I will argue. Yeah, you equated integrand, am I right? How did you equate integrand, and how can you say that these two are equal, am I right? This is equal to charge density at that point. Speak out. I will say maybe total integrals may be same. Okay. Suppose if you have written electric field at that r, if you have written rho at r, okay, how can you write? How can you what you call? How can you equate that one, isn't it? Speak out.
In function of r, sir. In function of r.
No. What I'm saying is we have equated the integrand, am I right? This part, am I right? This one. Now let me argue, maybe total volume integrals are same. Why these individual parts should be one-to-one correspondence? That's what I'm saying. Is that okay? I don't know why that question arised. Anyway, leave it. Yeah, speak out.
Sir, we are not getting properly question, sir.
No. Total, again, here I have an equality of two volume integral. If you have an equality of two volume integral, can you write whatever inside equal? That's my question. That's what we did here actually. Let me rub out. Okay, volume integral of.
If we differentiate both, then sir we will get integrants are equal, sir.
Integral of differentiation like that. So differentiation of integral.
Yes, sir.
D tau is equal to rho of r divided by epsilon naught. Okay, volume integral, isn't it? And we have equated this inside part actually. Yeah, anyway, just again, let me continue here. Here that again, I just write that question. But look at here. Here, in this definition of electric field, you will directly find that differential form of the Gauss law. What is this electric field for the charge density? Due to some charge density somewhere here, that's equal to 1 by 4 phi epsilon naught integral of, do you remember rho of r prime vector? Do you remember anyone? Rho of r prime vector d tau prime. Okay, d tau prime. Earlier it was integral of d tau. Do you remember? Del dot e d tau, not d tau prime. I mean that integral was with respect to x, y, z, not prime coordinate. But here d tau prime. This is the electric field due to, again, this is what you call, this is your principle of superposition actually. Is that okay? Into r cap by r square. R cap by r square. Speak out. Is that okay? Now let me take divergence of this one. Divergence of this one. Speak out. Let's equal to 1 by 4 phi epsilon naught. Look at here. Del dot integral of r cap by r square into rho of r prime vector d tau prime. Rho of r prime vector d tau prime. Look at here. Integral is with respect to primed coordinate, okay, which is a source charge actually. I mean, which is what you call r prime is the position vector of source charges, but this differentiation is with respect to this r. Remember, speak out. Are you getting the point? You have some charges here, okay, rho of r prime, okay. So that's how you define this is r prime vector, okay. But you are finding electric field somewhere else, okay. So this is italic r vector, electric field at this point. Electric field here. When you take the divergence, you take derivative with respect to this coordinate, remember. Derivative with respect to, again, derivative at that point with respect to this r, x, y, z. So this is dou by dou x, dou by dou y, dou by dou z. But this d tau, dx prime, dy prime, dz prime, that is the what you call, those are all the what you call, with respect to the what you call source charges. Find the difference. So because of that fact, we can take it inside. Is that okay? We can take it inside. Let me write again italic r vector, that's equal to r vector minus r prime vector. Is that okay? Speak out. I can take this one inside. Because this is with respect to some other coordinate. This integral is with respect to something else. Both are independent actually. So shall I take it inside?
Sir, so when we increases R, then rho of R increases.
Yeah.
But sir, E decreases. Electric field.
Why E should decrease? No. So don't you remember from the previous class this equation? Electric field due to some continuous charge distribution. But observe mathematics carefully. This was integral with respect to source point. This is differentiation with respect to field point. There are 2 points in space, am I right? This was integral with respect to source point. This was differentiation with respect to field point. That is the difference that you need to catch here. I mean, the rest of the thing you know, isn't it? This differential form, these things you know something, am I right? But try to generate much more idea here. Integral, while doing that principle of superposition, we have integrated with respect to source point. But while dealing with this Gauss law, we are differentiated with respect to field point. That's the difference. And this derivative is with respect to dou by dou x, dou by dou y, dou by dou z. This integral is with respect to dx prime, dy prime, dz prime. So x prime, y prime, z prime. So that's how you have to define what you call a source point. You have to define like this. Is that okay? We can take it inside. Once you take that one inside, speak out. What will happen here is, look at here, integral of rho of r prime vector d tau prime. This integral should be over all space, remember. Why? We don't know. Again, electric field at this point, it is due to this integral should be run over all space because charges may be there, many points, am I right? Each charges will produce electric field here. You have to integrate that one according to our principle of superposition, isn't it? Electric field at this point should be found by integrating with respect to what you call source charge throughout the region of the space actually. This is integral over all space actually. So integral over all space. So this is, again, look at here. This derivative is not with respect to r prime. That is with respect to r. That's why this part I can take it outside. I can write like this: divergence of r cap by r square. Check this out. This derivative will not operate on this one. I better to draw it separately. Okay, this is a source point, x prime, y prime, z prime. Is that okay? This is a field point. This is r prime vector. This is a field point. This is italic r. Am I right? This is x comma y comma z. This is r vector. This is our origin. Okay. Is that okay? You have electric field at this point r. Left hand side, you have taken derivative with respect to x, y, z actually. Okay. But this integral was with respect to x prime, y prime, z prime, because there may be different charges. We should integrate that one. We should integrate electric field due to each of them, each of individual, to find the total electric field, isn't it? This is a total electric field. I'm trying to explain one mathematics here, okay? So again, this is inside the integral only. What did this one speak out? What is that one? That's equal to 1 by 4 phi epsilon naught. So that's equal to 4 phi delta cube of italic r into rho of r prime vector d tau prime vector. Check this out. Speak out. So del dot E of r, practice this one. Okay, that's equal to 4 phi got cancelled. Okay, 1 by epsilon naught. Look at the integral carefully. Integral of del cube. Okay, integral of del cube of, how do you write italic r? Can I write r vector minus r prime vector? Or can I invert that one, r prime minus r, because Dirac delta, it's a kind of even function. You can interchange this one, isn't it? Yeah, let me write like this, later I will interchange, okay? Dirac delta of r vector minus r prime vector, okay? Rho of r prime vector d tau prime, again integral over all space. Speak out. Now, can I just interchange that r and r prime in the Dirac delta so that you can do that delta cube of r prime, which is variable. In the integration, this r prime is variable, remember. Is that okay? In the integration, r prime is variable. Grab this idea. Only rest of the thing you can manage, okay? Only small idea. R prime is variable. Rho of r prime d tau prime. Can I rewrite this one? Del cube of r prime minus some a vector, okay, into some function, okay, some function of r prime into d tau prime, okay. How do you write this one? Speak out. Integral that will choose this function at a, am I right? Speak out. According to property of Dirac delta. Speak out. I have interchanged this one because Dirac delta will allow that kind of rule. Integral with respect to r prime. Now Dirac delta will choose this function at r prime is equal to r. That is equal to rho of r divided by epsilon naught. What is here? Del dot E of r. Look at here. How our Dirac delta helped us to derive this one. Differential form of Gauss law. Is that okay? Do this one so that you will get a complete idea. If you do integration, with respect to what you are doing the integration. If you are doing differentiation, with respect to what you are doing the differentiation. Okay, two different things here. Source point and field point. Okay. X prime, y prime, z prime are for source point, prime thing. Okay. X, y, z are for field point. Okay. Now in this integral, okay, this is variable. Primed coordinates are variable. You have to treat this one as a constant, just like here I have taken. So this rho of r prime is just a function of some r prime, am I right? You can think like this. Just apply Dirac delta property, you got that one. That's why in space, if charge density is 0, divergence of electric field is 0.
Sir. Sir, here we are considering the charge density as a function of r. Can it be a vector function? I mean, in particular direction it is going to change, and in particular direction it is going to be constant like that.
Yeah, that can happen. That can happen. Charge density you can design, isn't it? But it is a scalar function.
Okay.
It is a scalar function. You have a divergence, it's a scalar, am I right? That's a scalar function because charges will add like a scalar. This again, if you have two charge densities, if you just merge in space, densities will add like a scalar, isn't it? It is a scalar function. Is that okay? Suppose if you have some charge density in space, I have equal charge density, I will merge that one. Then it's just an addition, isn't it? Charge density will be doubled, isn't it? Like that. It will add like a scalar. It's a scalar function. It's not a vector field. Okay? Be careful. But get one essence of this mathematics, that is, again, this integral was with respect to d tau prime. Just read out the earlier part, okay? Earlier part, how this equation came. But this differentiation is taken with respect to what you call field point. This integral was with respect to source point. And while doing this one, this r prime is variable. Dirac delta will choose this function at this point. Now look at here, there is no ambiguity in this one. This is another way of proving the differential form of Gauss law. Do this one again.